Okay, so in the last lecture we saw the concept of measurability. We will recall that and go on to look at some properties of measurable functions. The important result we will look at today is that any measurable function, any positive measurable function can be approximated by simple functions, which we will define later on. So, let us recall measurability. So, recall that we have a set X, we have a sigma algebra. So, this is a sigma algebra of subsets of X, and a function f from X to R or C complex plane is measurable. So, we will denote the abbreviation MBLE, measurable, if f inverse of any Borel set belongs to our sigma algebra for every B in B of R or B of C, right. Okay. So, we saw this yesterday in the last lecture. Let us look at some easy properties of this. One is, if let us write it as a proposition so that I can prove some of these things for you. If f and g are measurable functions, then so is f plus g, f minus g, f by g, f times g, and alpha times f, where alpha is a scalar. So, this can be either a real number or a complex number, right. Okay. So, we'll prove this. Proof of this is rather easy. So, let us look at just one of them. Suppose I know that f is measurable. So, this goes from f of xf to, let us say, R. Same proof will work for complex numbers, and I have g from x to the real line, both are measurable. Okay. I want to prove that f plus g. What can you say about f plus g? What can you say about f plus g? So, f plus g is a function from x to the real line. We want to check if it is measurable. Well, what do? We take inverse image of certain Borel sets and see if we land in f, right. So, recall that we do not have to look at all Borel sets in the real line, we need to look at only certain sets. So, we will look at sets of the form let us say minus infinity to alpha, where alpha is a real number. So, you look at f plus g and look at the inverse image of this set minus infinity to alpha, where alpha is a real number. Well, what is this? This is all those points in x such that f plus g at x, so that is fx plus gx, belongs to this set, which is same as saying this is less than alpha, correct. Well, I can write this as union over R in rationals x such that fx is less than alpha minus R intersection x such that g of x is less than R. So, if I do this, the set where f of x is less than alpha minus R, what is this? This is simply f inverse of minus infinity to alpha minus R. So, this belongs to script f. Similarly, the set where g of x is less than R, this is equal to g inverse of minus infinity to R, that also belongs to script f, because f and g are measurable. So now we go back to the previous situation. Here this set is written as a union of measurable sets, right, because this belongs to script f, this also set also belongs to script f, and so the intersection belongs to script f because script f is a sigma algebra, and then I am taking union over countable union, right, the union over rational. So this is a countable union. Countable union. So that will also belong to script f. So what we have proved just now is that if I look at f plus g and I look at the inverse image of minus infinity to alpha, then I belong to script f. This is true for every alpha in the real line, but then sets of this form generate the Borel sigma algebra that we have seen. So this implies that f plus g inverse of any Borel set. So this is the good sets principle we did in the last lecture. If I know that inverse image of collection of sets which generate the Borel sigma algebra is in script f, then it is true for all sets in the Borel sigma algebra. So this will belong to script f, which implies that f plus g is measurable. Okay, so now if you go back to the statement of the proposition, all this, so we just proved this for f plus g. Well, same thing can be proved for f minus g, or you start with alpha g, alpha f, take alpha to be minus 1, you will get this using f plus g, and same proofs work for f times g and f minus f by g and so on. You have to be careful about f by g. F by g is well defined only when g is non-zero. Okay, so this is defined only when g is not 0. Okay, if g is 0, then we can modify the definition, but we will come to that later. So this collection of measurable functions is a vector space. So that is what we have just proved, right? If I take xf and you look at the collection of real valued or complex valued measurable functions form a vector space. Well, so vector space is not important, but we will keep using all these properties of measurable functions at the time. So let us look at some examples. So I have a space x and I have a space f. I have the sigma algebra f, right? Sigma algebra. Take a set in the sigma algebra, okay, and define chi e. Chi e is called the indicator function or characteristic function of E. So this is 1 if x is in E, 0 otherwise. Okay, so this is called the indicator function or characteristic function of E. That is the definition. It takes 1 when x is in E, otherwise 0. This is measurable. If so, chi E is measurable if and only if E belongs to the set, E belongs to our sigma algebra. If E is not there, it is not measurable. So let us see why. So look at chi E. So chi E takes the values only 0 and 1, right? So it takes 1 when x is in E, 0 otherwise. So in the real line, it takes the values only 0 and 1. So if I take any interval, so let us take some interval AB inside R, and I look at the inverse image. So chi E inverse of AB. Well, what will this be? If the interval is like this, then it has 0, right, and suppose it does not contain 1, then the inverse image of this would be all those points x which are mapped here, which means which is 0. So that is when it is not in E, right. So this would be E complement if 0 belongs to AB and 1 does not belong to AB. Okay. What if 0 does not belong to AB and 1 belongs to AB? So then the interval is like this, right? So that will be all those points which are mapped to this interval, which is 1. So that is same as E. Only the points in E will go to 1. What if 0 does not belong to AB and 1 also does not belong to AB? Well, then the interval is something like this, and there is no range of, there is no value in this interval which is taken by chi E. So its inverse image is empty set. So these are the only possibilities. So this tells me that this is measurable if and only if these sets are measurable. These sets are in F. So chi E is measurable if and only if E complement E are in script F, right, which is same as saying E is in script F. So let us go back. This set, this function is measurable if and only if the set E is measurable. So that is one of the simplest examples of measurable functions. Now suppose, so let's look at some other class of functions. Suppose I have f from xf to r or c measurable. Okay. Let capital phi be a function from r to r or c, okay, or it could also be from c to r or c, measurable, continuous. So these are continuous functions. Let us say phi is continuous. Then if I compose these two functions, so I am going from x to r or c by f, and from here to r or c by phi, and I am looking at the composition. So what is the composition? Composition is phi composed with f. This is a map from xf to r or c, right? This is measurable. Okay, so we have f measurable, phi a continuous function, and we are looking at the composition. We want to say that is also measurable. Well, how will we do that? So let's take some set which is inside R or the complex plane, and we look at inverse image, phi composed with f inverse of E, right. So we don't need to take any Borel set, remember, because we need to take only open sets. So this is nothing but, because the inverse, the way it is defined, it would be phi f inverse composed with phi inverse of E, which is equal to f inverse of phi inverse of E, and this is an open set. Why? Because phi is continuous. So this is an open set, and so this will belong to the Borel sigma algebra of R, and so f inverse of that would belong to script f, and so this is measurable. Okay, so we will continue with some more such things. So let's write a proposition. Suppose Fn, so this is for n 1, 2, 3, etc., infinitely many. Fn's are measurable. So let us say it takes values in closed minus infinity plus infinity. So let me say a few things about closed minus infinity plus infinity before we go ahead. So this is the extended real line, Here the usual arithmetic operations happen. If I take 0 into infinity, this is assumed to be 0, 0 into minus infinity is also 0, but terms of the like infinity minus infinity does not make sense, okay, does not make sense. What is the sigma algebra here? So, I have a Borel sigma algebra of okay. So, I have a Borel sigma algebra for minus infinity infinity closed. Well, what do? We take usual open sets in the real line along with sets of the form minus infinity to alpha open to infinity closed, okay. Then you generate the sigma. So, these are the new open sets. You generate the sigma algebra using this, generate the sigma algebra with these sets, okay. So, then you have sigma algebra here, and measurability here would mean Fn inverse of any set belongs to script f as long as that set belongs to the Borel sigma algebra of minus infinity infinity, right, the usual definition. So, I have a sigma algebra here, I have a sigma algebra here, I take the inverse image, I should be here, okay. So, I assume that there are measurable functions, countably many, then supremum Fn n greater than or equal to 1 is measurable, okay. Similarly, lim sup of Fn is also measurable, okay. So, let's prove this, okay. Proof of this is very easy. So, let's call that g of x equal to supremum over n greater than or equal to 1 Fn of x, right. So, this supremum of Fn is a function which is g of x, which at each point x is simply the supremum of the values of Fn x. These are values, taking values here, right. Now, consider the set x such that g of x is greater than alpha, okay. Well, what will this be? This is simply, so g of x is greater than alpha, meaning the supremum is greater than alpha. Supremum is greater than alpha would mean that one of them is greater than alpha. So, that is same as saying this is the union all sets where Fn is greater than alpha. So, let's see why this is true. So, if I take an x on the left hand side, then I know g of x is greater than alpha, and so the supremum is greater than alpha. So, there will be one Fn for which it is greater than alpha. So, it could be some Fk, it could be some Fk plus 1, etc. So, that will be here. Similarly, if the point is here, that means for some n Fnx is greater than alpha, and so obviously supremum will be greater than alpha. Well, but what happens to these sets? Fn's are measurable, so these sets will belong to script f, and script f is a sigma algebra. I am taking a countable union, and so this would be in script f. So, this implies that G is measurable. Similarly, prove that infimum of Fn's are also measurable, okay, same proof. So, this would implies that lim sup of Fn, well, how is this defined? So, let's call this h. How is this defined? H of x would be lim sup of Fn of x, right. What is this? This is infimum over n supremum over k fkx, right. That is the definition of lim sup. These are measurable functions, these are k greater than or equal to n. So, these are measurable functions for each n, right, call that gn if you like. Then I am taking infimum over it. So, infimum of measurable, supremum of measurable functions is measurable. So, GNs are measurable. Then I take the infimum, that is also measurable. So, this is measurable. Corollary, if fx equal to limit n going to infinity fnx exists for every x in x and fn are measurable, then f is also measurable. Okay, that is because lim sup will be equal to limit, right, because the limit exists. So, if you take limit of measurable functions, you will get a measurable function. Definition. So, a simple function is, so definition, simple function is a measurable function whose range is finite. That is, let us say I have a space X and a sigma algebra S. So, I look at real valued or complex valued, of course, range of S is finite. So, range of S is finite. So, range of S will be finitely many elements from the reals or complex. So, let us say alpha 1, alpha 2, etc., alpha k. So, I can write, so this is supposed to be measurable, we can write S of x equal to summation j equal to 1 to k alpha j chi ej of x. So, remember chi ej was 1 if x belongs to ej, 0 otherwise. Okay. What are ej's? Ej would be the set where S takes the value alpha j, right. So, this is simply S inverse of the singleton alpha j. So, Ej are measurable, Ej are measurable because S is a measurable function, this is a Borel set, this is a Borel set, and so when I take the inverse image I will get a measurable set. So, it is a finite linear combination of simple indicator functions, right. So, finite linear combination of characteristic functions, that is what a simple function means. Okay. So, the main result we want to prove today is that any positive measurable function is a limit of simple functions. So, you can think of simple functions as step functions on the real line or an interval. They are the building blocks, and we prove that any measurable function is actually a limit of simple functions, which will actually help us in defining integration of positive functions, and you will see that there are certain theorems which allow us to interchange the integral and the limit follows from this definition very easily, and that is a big advantage we will see as we go along. Okay. Okay. So, let us start with an exercise. If g of x equal to summation alpha j chi ej of x j equal to 1 to k is measurable if and only if ej are measurable. So, let us recall the what we did earlier. Here the ej's were, these are disjoint sets because alpha j are distinct elements. So, when I look at the inverse image, they are disjoint sets. In the exercise, we are not assuming ej's are disjoint, we are not assuming ej are disjoint. Okay. but you can disjointify them. Okay, so hint is to disjointify, hint disjointify Ej. Okay, so here is the promised theorem. This is very important, first non-trivial theorem in this course. So let f from x f to 0 infinity, so positive measurable be measurable. Okay, then there exist simple functions Sn such that 1 0 less than equal to S1 less than equal to S2 less than equal to S3 etc. So that is Sn are increasing to limit of Sn at x equal to f of x for every x. So any positive measurable function is an increasing limit of simple functions. Moreover, if f is bounded, so the measurable function you started with is bounded, then the convergence is uniform. So if the function is bounded, okay, it will be used at some point, but the main part is this part, that you have a sequence of simple functions converging in an increasing manner to f, right. Any positive measurable function is an increasing limit of simple functions. So remember, simple functions you think of as slightly more generalized than the step functions. Recall that when you did Riemann integration, you had step functions and you approximated the integral of the function via step functions. We are doing something similar. It's just that you have more general functions than step functions, but the range is still finite and they are called simple functions. And any positive measurable function you can actually approximate by simple functions, and that will help us in defining integration. So let us prove this and then we will go ahead. So proof is rather simple, but one should try to understand this in full detail. All that we do is define the sequence Sn of x to be, okay, k minus 1 by 2 to the n. If k minus 1 by 2 to the n less than or equal to f of x, strictly less than k by 2 to the n. Well, where does k go from? K goes from 1 to all the way up to n times 2 to the n. So when k is n times 2 to the n, you have f of x to be less than n, and you take n if f of x is greater than or equal to n. So that defines my simple functions. Well, first of all, this is simple. So why is that? Sn are simple functions. Why is that? Because I can write Sn of x to be k minus 1 by 2 to the n, that is the value of Sn if f falls here. So that is same as saying you look at the indicator of the set k minus 1 by 2 to the n less than or equal to f of x, strictly less than k by 2 to the n, right. So if x falls in this set, then I will have 1 here and 0 in all other places, right. So I will get k minus 1 by 2 to the n. So that is summed up from k equal to 1 to n times 2 to the n, and when f is greater than n, I have n, right. So plus n times indicator of the set x such that f of x is greater than or equal to n. So, this is a linear combination of indicator functions, right. So, to say that it is measurable, all we have to do is to check that these sets are measurable. Well, what is the set x such that k minus 1 by 2 to the n is less than to f of x less than k by 2 to the n? Well, this is nothing but f inverse of closed at k minus 1 by 2 to the n comma k by 2 to the n, and this is a Borel set, okay, and so this set would be measurable. So, this implies that SNs are measurable. So, next we prove that Sn converges to, okay, so let's try to draw this picture a little bit. So, okay, 0, 1, 2. So, let us look at what is S1 of x. So, S1 of x would be 0 if 0 less than or equal to f of x strictly less than 1 by 2, right. So, remember k goes from k goes from 1 and 2, okay, and it would be half if half is less than or equal to f of x less than 1, and 1 if f of x is greater than or equal to 1. So, what we are doing is we are looking at the range of f and then decomposing it. So, we go from 0 to half. If f falls here, then we take 0. If f falls here, then we take half, and if f is greater than 1, we take 1, okay. So, the set where f is between 0 and half, so that would be the inverse image of this set, right. So, that could be some set here, some set here, some set here. There my symbol function is 0. Now, if you look at this area, well, I will get some set here, perhaps some set here, and so on, and here I have half, and if f is greater than 1, I will get just 1. So, at some place I will have just 1. Well, let us look at what is S2x. S2x, so remember k is 2, so k goes from 1, 2, etc. 2 into 2 to the 2, which is 8. So, I will go up to 8. So, I will not write everything. So, I will have 0 if 0 less than or equal to f of x less than 1 by 4. I will have 1/4 if 1 by 4 less than or equal to f of x strictly less than half. I will have half if half less than or equal to f of x less than 3 by 4. So, I will write one more 3 by 4 if 3 by 4 is less than or equal to f of x strictly less than 1, and so on. So, it will go up to 2, right, f of x less than 2, and f of x is greater than 2, the symbol function is 2. Okay. So, let's see what did we do. Initially we had 0 to half, half to 1, that became 0 to 1/4 and 1/4 to half. So, this interval got divided into 2. Similarly, this interval got divided into 2, and this interval got divided into equal parts, 4 equal parts, and we have 3 and so on, okay. So, in the first step, if f is between 0 and 1/4, then the symbol function is 0, but if f is between 1/4 and half, then we take the lower end point 1/4, okay. So, remember in the first case it was 0, between 0 and half the symbol function was 0. In the next case it may go up, but it is either 0 or slightly more than 0, right. So, it is increasing. So, if you write down S1, S2, S3 and so on, you will see that it is increasing. It always stays below f, and what we are doing is we are decomposing the range of f into smaller and smaller intervals as we go along. That will give us simple functions Sn of x which is always less than or equal to f of x, because it is always the lower endpoints of various intervals which we are looking at. And more importantly, if I take an x, there exists some k and n such that k minus 1 by 2 to the n is less than or equal to f of x less than k by 2 to the n for some k and n, which tells me that if I look at the difference between f of x and that particular Sn of x, well, this is of course f of x minus Sn x, but f of x is here and the value of Sn x is, so this is f of x minus the value is k minus 1 by 2 to the n, the lower end point, right. So, this will be less than or equal to 1 by 2 to the n always, because f of x is greater than less than k by 2 to the n, right. So, let me write one more step just to be clear. So, this is less than k by 2 to the n minus k minus 1 by 2 to the n equal to 1 by 2 to the n, and this goes to 0 as n goes to infinity. Okay. Remember, Sn's are increasing. So, if I look at fx minus Snx, fx minus Sn plus 1x, this is of course going to be less than or equal to f of x minus Snx, right, because Sn is smaller than Sn plus 1, and so this goes to 0. So, this implies that limit of n going to infinity Snx is actually equal to f of x for every x. If f is bounded, then that greater than or equal to n part does not arise. So, let us see. Yeah. So, for a large n this will not be there because f is bounded. So, f will be less than or equal to some fixed m. So, only these are the values of, only these will be the values of the simple function. So, that will tell me that if f is bounded, modulus of Snx minus f of x, and I take supremum over x in x, this would be less than 1 by 2 to the n for all large n. Okay. That implies Sn converges to f uniformly.